So instead of looking at the options, let's try and name this organic compound ourselves, right? And then we'll just compare our solution to the options we have. So how many carbons do we have? We have 1, 2, clearly. So we know fully well that the name is supposed to start with eth, right? And then now we can then look at the functional group so that we can know how our name is supposed to end with. So we have a carbon that is bonded to an oxygen and another hydrogen, right? If this carbon was bonded to an oxygen and 2 other carbons, then it was going to be a ketone, right? For a ketone, we need something of this manner, right? This would be a ketone. So it's clearly not a ketone. And then instead of O, if we had OH, then it will be an alcohol, right? But then we don't have that. So it's clearly not an alcohol. And then if this carbon was bonded to an oxygen and an OH, then it was going to be an ester, right? And then it's clearly not an ester. This carbon is only bonded to an oxygen, another carbon, and a hydrogen. That's an aldehyde. So our name will end with ENAL. So we have ethanol, and that is option D. And then 1.2 says, which of the following represents a balanced equation for the combustion of octane? Again, instead of looking at the options, let's have an equation for the combustion of octane, and then we'll just compare our solution with the options. So we have C8H18 plus O2 giving us CO2 plus H2O. When you have combustion, the products will always be CO2 and H2O, right? So the problem here is to balance the equation, right? So let's go ahead and try do that. So clearly on the left side, we have 18 carbon atoms, right? And then on the right hand side, we only have 1. So how do we balance that? We put a coefficient of 8, and there we go. Now we can move to hydrogen. You always have to start with carbon, hydrogen, and then oxygen. If you do it in that way, it's way easier compared to if you just start with oxygen, I suppose. Let's go ahead. So for hydrogen, we have 18 atoms, and then on the right hand side, we have only 2. How do we balance that? 18 divided by 2 is 9. So we put a coefficient of 9 here. Now let's move to oxygen. We have 2 atoms of oxygen on the left hand side, and then on the right hand side we have 8 multiplied by 2, that will be 16, right? Plus 9 oxygens, right? So we have 16 plus 9, which is 25, right? And then here we have 2 oxygens. So how can we balance this oxygen? On one side we have 25, on the other side we have 2. If we put 25 divided by 2 here as a coefficient, then the oxygens will be balanced, right? But then you know fully well that on a chemical reaction, we're not supposed to have fractions. So if we multiply everything out by 2, then we're going to have our balanced equation. So if we do that, we're going to get 2 C8H18 plus 25 O2, giving us 8 multiplied by 2, that is 16, right? 16 CO2 plus 9 multiplied by 2, that is 18. So we have 18 H2O. So now we have the equation of our combustion reaction, and we can look for the corresponding option, right? So option number A, we have 2C8H18 plus 25, and then we have 16, we have 18. So it seems like option A is the right one, right? So 1.2, we go in with option A. Now let's do 1.3. 1.3 is saying, which of the following compounds will decolorize bromine water the fastest under normal conditions? So bromine water is just a solution of bromine, right? So the way you approach this question is, what would easily react with Br2, right? A says ethane. We know that ethane is unsaturated, so it can easily react, right? So at this point, ethene, we can work with it. And then B says ethanol, that cannot easily react because it's saturated. Same with ethanol and ethane, right? So for 1.3, a compound that will decolorize bromine water the fastest under normal conditions would be ethane. That is because it is unsaturated and it will readily react compared to the other compounds. Right, now let's do 1.4. 1.4 is saying 3 catalysts are used separately to increase the rate of a reaction, of a hypothetical reaction. In the diagram below, E1, E2, and E3 represent the effect of each catalyst on the activation energy. The activation energy being E0, right? I just circled it. And then which of the following is the activation energy for the reaction with the highest rate? So a reaction with the highest rate. So a reaction with the highest rate allows more number of molecules to have required energy, right, to be above the activation energy. So we're saying that the activation energy is here at E0 or EO, right? Before the addition of catalyst E3, only this number of particles had enough energy to react, right? But then after we add E3, more number of particles have enough energy to react. But then when we use catalyst E2, even more particles have enough EK to react, right? But you can see that when you use E1, even more particles can react, right? So the highest rate, we associating it with the activation energy E1. It lowers the activation energy way more than E2 and E3, because you can see that on the x-axis we have EK, right? At E1 we are here, and then E2 requires just a bit more energy, and then E3 requires even more energy. But then E1, it really lowers the energy more than all the others, right? Let's do 1.5. So 1.5 is saying 50 centimeter cube of 0.1 mole per decimeter cube solution of hydrochloric acid is poured to 5 grams of zinc, which is inside a glass beaker at room temperature. Which of the following factors will not increase the initial rate of the reaction? I've done a video on rate of reactions and factors that affect that. So if you want to watch that, you can go on a playlist titled rate of reactions and watch that video. But then let's answer our question here. So the keyword, which is in bold, right? Which factor will not increase the initial rate of the reaction? If you grind the zinc into powder, that will obviously increase the rate of the reaction because you're increasing the surface area. And then using 30 centimeter cube of 0.2 mole per decimeter cube of hydrochloric acid. So let's see how that affects the rate of the reaction. Initially, for hydrochloric acid, we had 50 centimeter cube and 0.1 mole per decimeter cube concentration. So let's find the number of moles there. So the number of moles is equals to the concentration multiplied by the volume. So that will be 50 divided by 1000 multiplied by 0.1. And that is 5 times 10 to the minus 3 moles, right? Let's see how that compares with 30 centimeter cube multiplied by 0.2. That is the number of moles will now be 6 times 10 to the minus 3. So clearly, if you choose to use that volume and concentration, you will increase the number of moles, right? And increasing the number of moles increases the rate of the reaction. So B is not what you're looking for. And then C says increase the temperature of the acid solution to 50 degrees Celsius. If you increase the temperature, you increase the rate of the reaction. So C is not our option. Now we know that the option we're going for is D, right? But then let's just look at the question and see why it is true. So it is saying using 100 centimeter cube of 0.1 solution of hydrochloric acid. So let's see how that affects the concentration. So we have 100 divided by 1000, right? Let's see how that affects the number of moles. So we're gonna have the number of moles being equals to 100 divided by 1000 multiplied by 0.1, right? Concentration multiplied by the volume. And then if we do that, what am I getting? We get in 1 times 10 to the minus 2 moles, right? So initially we had 5 times 10 to the minus 3. Now we have 1 times 10 to the minus 2, right? So to the minus 2 is definitely greater to the minus 3, right? So for option D, we are increasing the number of moles and the rate of reaction will go up. And then here we're looking for an option that doesn't increase the rate of the reaction. 1.6 says the graph below represents the change in the rate of a reaction versus time for the reversible reaction that takes place when an amount of hydrogen gas and iodine gas was sold off in a container. And then there we have an equation, right? And now it says that what change in the conditions was made at 10 minutes to change the rate of the reaction as indicated on the graph. So let's go to the graph and look at 10 minutes. So if all the time, if these lines for the rate of the reactions of the forward and the reverse reaction, right, they go up simultaneously and there is no sudden drop in one of the lines, then the change was a catalyst. It's only a catalyst that will have that sort of an effect, right? Because if you increase the temperature, depending on whether the forward reaction is endothermic or exothermic, then one reaction is supposed to be favored than the other. And even if you play around with all the factors, you're supposed to have a sudden increase followed by a sudden drop, right? But then only when you add a catalyst, they will all increase and there is no sudden drop. So now we're looking for a catalyst, and that is option A. Now we can go to 1.7. 1.7 is saying consider the 4 different solutions. Which of these solutions is a dilute weak acid solution? So dilute weak acid solution. Let's look at the options we have. A says 0.1 mole per decimeter cube of HCl solution. We're looking for dilute and weak, right? We know fully well that HCl is not a weak acid. You might choose to dilute it with water, but then it's not a weak acid by nature. So HCl cannot be part of our solution. And then B says 5 mole per decimeter cube of CH3COOH, right? We know that CH3COOH is a weak acid in its nature, right? So now it satisfies the weak criteria. But then is it dilute? We have 5 moles per decimeter cube. That is very, very concentrated, right? So it cannot be dilute. So option B cannot be our answer. Now let's look at option C. Option C, we have oxalic acid. Oxalic acid, it satisfies the criteria of weak, right? We know that it's a weak acid. And then let's look at whether it's dilute or not. 0.5 mole per decimeter cube. It's sort of dilute, right? It's not very concentrated compared to B. Here we can say that we're considering the oxalic acid, and let's look at option D. Option D, we have NaOH, which is a base, right? So obviously here our answer is C, because it's dilute and it's weak. Maybe if there was another weak and more dilute acid, then we would go with it. But then clearly it is the only one that is dilute and weak. Let's see what 1.8 has for us, right? So it is saying that the following equations represent 2 hypothetical half reactions. The reduction potentials are also provided. Here we have x2 plus 2 electrons giving us 2x minus, right? And then we have the reduction potential. And then on the reaction below, we have y plus 1 electron obviously giving us Y. And then we have the reduction potential. And then the question says, which of the following substances from these hypothetical half reactions will be the strongest oxidizing agent? So now, as you can see, the only information we have is the reducing potentials, right? Which one will be the strongest oxidizing agent? So now the question is, what is the relationship between the reduction potential and the state of being an oxidizing agent, right? So we know fully well that the higher reduction potential, right? The higher the reduction potential, the stronger an oxidizing agent is, right? The stronger an oxidizing agent is, right? So here, let's look at which one has the highest reducing potential, right? And from there, we will know which one is the strongest oxidizing agent, right? So let's, look at our equations again. So clearly here on equation 1, x2 plus 2 electrons giving us 2x minus has a reducing potential of 1.9 volts, right? Compared to the second equation, which has a reducing potential of minus 2.8. So on our first equation, are we then picking x2 or x minus? We know that an oxidizing agent gains electrons, right? So clearly x2 is the one gaining electrons to form 2x minus, and not the other way around, right? So here we go in with option B, because that's where we have x2. 1.9 is saying, which one of the following combinations correctly shows the products formed during the electrolysis of brine, right? If you don't know what brine is, then how can you possibly answer this question? That's what you're here for. So brine is NaCl solution, right? It's an NaCl solution. So the equation of this reaction is a 2NaCl plus 2H2O, giving us Cl2 plus H2 plus NaOH, right? So what is going to happen is that at the anode, we are going to have 2Cl minus, giving us Cl2 plus 2 electrons. And then on the cathode, we're going to have 2H plus 2 electrons, giving us H2, right? This is what's happening in the grand scheme of things, right? Just to make a summary of the reaction. So clearly, now we're looking for an option that says at the anode, we get chlorine, and then on the cathode, we get hydrogen, right? So yeah, option A says that on the anode, we get in chlorine, and then on the cathode, we get in hydrogen, right? So the answer here is option A, based on these brine equations that we have. This is the overall reaction. This is what takes place at the anode, and then this is what takes place at the cathode. Now let's do 1.10. 1.10 says, study the diagram below illustrating the industrial production of product C. What is product C? Stories. And then which process is used to produce product C? Okay, so let's look at the first step before we get ahead of ourselves. So we have NH3 plus O2, and then somehow we're going to have H2O plus something here, right? This is actually Ostwald process, right? What we have here is NO, right? So what we have here is NO, and then the equation is unbalanced. You have to do that work, and then from having NO, then you get NO plus O2, and then we're going to get NO2. So here at B, we have NO2, right? And then at C, we have NO2 plus H2O, and we're supposed to get HNO3. Like I've said, it's Ostwald process, right? That is option number D. Which letter represents an alkene, right? So what we want to do here is to have a functional group of an alkene, right? So we know that in an alkene, we have a double bond, right? And then the name ends as E-N-E. So when we go to our table here, whatever that has a double bond or the name ends with E-N-E, we know fully well that that's an alkene, right? Clearly on A here, we have a double bond. So as soon as we see that there's a double bond, we know that it's an alkene, right? So right now we can just write A. And then B, we don't have any double bond between carbon atoms. And then on C, we have a double bond here. So C is part of our solution. So for 2.1.1, we have A and C. And then for D, there's no double bond, and then it doesn't end with E and E. And then for E, no double bond. And then for F, there's a triple bond, right? And that's not what we're looking for. So the answer for 2.1.1, we just have A and C. Now let's go to 2.1.2, which letter represents a ketone. Again, we're going to look at the functional group of a ketone. For a ketone, we need something like this, right? We need a carbon that is bonded to an oxygen and then bonded to two other carbons, right? So if we see something like that, or a name that ends with O-N-E, then we know that we have a ketone, right? So for A, we already know that A is an alkene, so there's no way it can be part of our solution. But then if you look at B, we have a carbon here bonded to an oxygen and two other carbons. So clearly B is our ketone, right? So for 2.1.2, we have B. C is also an alkene, so it cannot be part of our solution. D doesn't have what we're requiring. E and F also doesn't have what we're requiring. So now we can go to 2.1.3. 2.1.3 says, let's look for a compound with a general formula CnH2n minus 2. Right? If you're not already familiar with this, this is an alkyne, right? The name ends with Y-N-E. Another way of identifying it, we have triple bonds, right? So a carbon is bonded to another carbon, and there's triple bonds in between the two. So again, we go to our table and we look for that. A cannot be part of our solution. B cannot be a part of the solution. C also cannot be part of our solution, right? And then D, we don't have a triple bond or Y-N-E, right? So that cannot be part of our solution. For E, no triple bond. And then F, that's where we have our triple bond, right? You can see it here. So for 2.1.3, we can put F as our answer. Right? The way of approaching this problem, you have to know exactly what you're looking for, right? It becomes extremely easy when you do that. And then 2.1.4 says, let's look for a structural isomer of octanoic acid, right? Octanoic acid. So for an acid, if we're looking for a structural isomer, we're looking for another acid or we're looking for an ester, right? Because acids and esters are functional isomers. So if the structural isomer is an acid, then we should find something of this manner, right? Or something that ends with the name acid, right? And then if it's an ester, then we're looking for something like this, right? Or a name that ends with ATE, right? A cannot be part of our solution, B cannot be part of our solution, C cannot be part of our solution. But obviously, if you look at D, this name here ends with ATE, right? And then not only does it end with ATE, it also has 8 carbons, right? Like the octanoic acid, which is of our interest, right? So the answer of 2.1.4, we are going with D. And then now we can do 2.2. 2.2 starts by saying that let's write down the UPEC name of compound A. So what you want to do first, step number 1, is that to identify the longest carbon chain, right? So we have 1, 2, 3, 4, 5, 6. Even if you take any other way, you'll end up with 6, right? So now we know that as part of our name, we should have hex. Now we are going to look for the side which leads us to the functional group first. Obviously, if we start counting from this side, if we say 1 here, 2 here, and then we have our functional group, right? So it will say hex 2 in, right? But then if you start on the other side, you'll say 1, 2, 3, 4, and then it will be on carbon number 4, right? So we prioritize the side that leads us to the functional group first. So we have hex 2 in, right? Now we can look for the branches. So let's name our carbons first. So that is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6, right? On carbon number 4, we have a branch. We have 1 carbon, right? And then on carbon number 5, we also have a branch. So now we can say 4, 5 dash. We don't say methyl, right? Because we have 2. Instead of saying methyl, we say dimethyl. 4, 5 dash dimethyl, right? And between words, there's no need to put a dash. Now we can go and do 2.2. 2.2.2. We need the UPEC name of compound E. So let's go look at compound E. Let's look for the longest carbon chain. So if we say this is 1, 2, 3, 4, 5, 6, 7, and then if we take this way and we keep going forward, we get 6, right? So we can conclude that the longest carbon chain has 7 carbons. So what is 7? We know fully well that 7 is hept, right? So we have hept. And then let's look for the functional group. It's an alkane, right? Every carbon is essentially the functional group. So we don't put anything there for an alkane. We can just say heptane. You only put something when you have an alkene or you have an alkyne. And then all the other complicated organic compounds with other functional groups. Now you will realize that we have an ambiguity here. We have a halogen on the second carbon, right? When you start counting from the left, and then we have a branch on the third carbon when you start counting from the right, right? So which one do we prioritize between the carbon and the halogen? Between the carbon and the halogen, we prioritize neither. So whatever that comes first, it's what we take, right? If a certain path gives us a methyl first, then we're going to take methyl. But then if we start counting from the left, then we get to bromo first. So we're going to take bromo, right? But then you can get a situation where on the left path, you get to bromo, and then on the right path, you get methyl. What do you do when you have a situation like that? Then you have to check the alphabet, right? You have bromo and methyl. So you would take bromo because alphabetically wise, bromo comes first. But then now because bromo is on the second carbon from the left, and then the methyl is on the third carbon from the right, you just take bromo automatically. And then if the methyl was on the second carbon and the bromo was on the third carbon, then you would take the path that leads to the methyl first. So we have carbon 1, 2, 3. So on carbon 2 and 3, we have 2 halogens, right? So we're gonna have 2,3 dash dibromo, right? Because we have 2. And then we can then look for the branch, right? Carbon number 4, carbon number 5, and then on carbon number 5, we have methyl, right? So we're going to have dash 5 dash methyl. And then there goes our UPEC name. And then last but not least, we have 2.23, which says let's write the UPEC name of compound F. In compound F, we have an alkyne, right? Because we have an alkyne, we have a functional group. So naming will be much easier because we always prioritize the functional group. So we're going to start naming from this carbon here. So we're going to have 1, 2, right? And then 3, 4, 5. Even if you go up, you still have 5 carbons, right? So now it's easy to see that we'll have pent, right? And then now let's look for the position of the functional group on the second carbon. So we're going to have pent 2YNE. Now we can look at the branches and so on. We have a branch on the 4th carbon. So we're going to have 4-methyl. Now let's do 2.3. So 2.3 says that compound D is prepared by reacting two organic compounds in the presence of an acid as a catalyst. And then 2.3.1, let's write down the structural formula of compound D. So let's go and look at compound D. So compound D is pentyl propanoid, right? We know that if it ends with propanoid, it's an ester, right? One thing about an ester, the first part of the name is the alcohol and the last part of the name is the acid. So let's write the structural formula. We know fully well that pent is 5, right? So we're going to have 1, 2, 3, 4, 5. We're saying that the first part is the alcohol, right? So here we were supposed to have OH, but then when it forms an ester, it loses this hydrogen here. And everywhere else where I'm putting a dash, you fill that with hydrogens, right? And then the last part, propanoid, that is the acid. So propanoic acid was supposed to look like this, right? But what happens is that when it forms an ester, it loses this OH here, right? The alcohol loses an H, and then the acid loses an OH, and then the byproduct is then H2O, right? So let's put it in our structural formula. So here we're gonna have dash a carbon, an oxygen, carbon, and then there we go. So like I said, everywhere when there's a dash, we just put hydrogens, right? For the sake of time. Now let's do 2.3.2. 2.3.2 says the UPAC name of the organic acid used to prepare compound D. Yeah, we went through it, right? I say that the last part comes from the acid and the first part comes from the alcohol. It is saying prop, so we know that the acid that was used there should be propanoic acid, right? So 2.3.2, the answer is propanoic acid. And then if the question was saying let's name the alcohol, then it was going to be pentanol. 2.3.3 says let's name or give the formula of the catalyst that is used, right? In esterification, we always use H2SO4 or sulfuric acid. If a compound has a higher vapor pressure, what does that say about the boiling point? What does that say about the melting point? Before we do that, let's do 3.1, which says let's define the term melting point. So melting point is the temperature at which the solid and liquid phase are at equilibrium. The temperature at which the solid and the liquid phase are at equilibrium. And then now 3.2 says which one of C or D has the higher vapor pressure? Give a reason for your answer. So here we are given compounds and their melting point. So for you to be able to answer this question, you need to know the relationship between vapor pressure and melting point. So what is the relationship between the two? We know fully well that the higher the vapor pressure, the lower the boiling point. The same is true for melting point. The higher the vapor pressure, the lower the melting point. So between C or D, the one with the lower melting point has the higher pressure based on this relationship we're proposing. So which one between C or D has a lower melting point? It's clear to see that C has a lower melting point, right, at minus 16 degrees Celsius versus D, which has a melting point of 16.7. So our answer for 3.2, we would say C. And then why are we saying C? We are saying C because it has a lower melting point. We know fully well that the higher the vapor pressure, the lower the melting point. 3.3.1 says let's define the term structural isomer. So structural isomers are organic compounds that have the same molecular formula but different structural formula. The same molecular formula but different structural formula. Right? And then 3.3.2 says explain why B has a higher melting point than A, referred to structure, intermolecular forces, and energy in your explanation. So A and B are structural isomers. They have the same molecular formula but different structural formula. So let's look at A. A is clearly branched, right? It says 2-methylhexane. So on the second carbon, we're supposed to have a branch. And then B just says heptane. So B is a straight alkane. That is the only difference between the two. And we're going to use that to explain our answer. So we are already told that B has a higher melting point. If B has a higher melting point, we will know consequently that it has a lower vapor pressure, right? Because the higher the vapor pressure, the lower the melting point. So here we have higher melting point, so we need lower vapor pressure. But why does it have lower vapor pressure but A doesn't have? So the difference between A and B is that B is less branched, right? As we are proposing, B is a straight alkane while A is a branched alkane. But then if it's less branched, then what will that mean? That will mean that we have stronger intermolecular forces. So we have strong IMF. Right? And then stronger intermolecular forces will mean that we need more energy to break bonds in compound B, right? So more energy required to overcome IMF. Just to recap, we are comparing A and B. B has a higher melting point, so we know that it has lower vapor pressure. If it has lower vapor pressure, it has stronger IMF, and if it has stronger IMF, then it requires more energy to overcome the intermolecular forces, right? But then what's the difference between A and B? The only difference between A and B is that B is less branched. So this tells us that if you have two structural isomers, the one that is less branched will always have a higher melting point versus the one that is more branched. Now let's do 3.4. 3.4 says let's explain the difference in the boiling points of C and D, referring to the intermolecular forces and the energy in our explanations, right? Let's go back to the basics real quick here. So we know that compound C, right, is an alcohol, and then compound D is an acid, right? So because compound C and compound D are with an alcohol and an acid, we know fully well that they both possess hydrogen bonding, right? We know that they both have hydrogen bonding, right? So we can say that they both have hydrogen bonding. But then if they both have hydrogen bonding, then why do they have different melting points and consequently different boiling points? That is because compound D, right, which is our acid, has two sides of hydrogen bonding versus compound C that has only one side of hydrogen bonding. Now the question you're asking yourself might be, wait a minute, what are we talking about? Why are you saying compound D has two sides of hydrogen bonding? That is because acids can go under a process called dimerization, right? And then alcohols cannot. So we say that compound D has two sides of hydrogen bonding, right? If it has two sides of hydrogen bonding, then what does it mean? It means our compound D has stronger intermolecular forces, right? And then what do we know about compounds that have stronger intermolecular forces? They require more energy. They require more energy to overcome the intermolecular forces. And if it requires more energy to overcome the intermolecular forces, then the boiling point of compound D, right, will be greater than that of compound C. One in an unsaturated hydrocarbon, and compound X, a saturated hydrocarbon, reacts with bromine as represented by the incomplete equations below. 4.1.1 give a reason why but1-in is classified unsaturated. It is classified unsaturated because it has double bonds, right? If an organic compound has double bonds or triple bonds, then it is unsaturated, right? It can still go under addition reaction. So 4.1.1, it contains a double bond. So it contains a double bond. Now let's move to 4.1.2, which says that what type of reaction, addition or substitution, takes place in the following. Reaction 1. Reaction 1, we have but1-in plus bromine, right? Because this organic compound here is unsaturated, it can only go under addition reaction, right? And then now we can move to reaction number 2. Reaction number 2, we have X, which is said to be a saturated hydrocarbon, right? So it's an alkane, and then we are adding bromine. So an alkane can only go elimination or substitution, right? But then we are already told here that we have to choose between addition or substitution, right? So clearly our answer here will be substitution. So for B, we have substitution. 4.1.3, write down the reaction condition necessary for reaction 2 to take place. For reaction 2 to take place, we need heat, or we need sunlight, but from sunlight we're still looking for heat from the sunlight, right? Or we need UV light. And then 4.1.4 says write down the UPEC name of reactant X, right? Reactant X is a hydrocarbon, and when we substitute bromine we get 2-bromobutane, right? It should be quite clear that the UPEC name of reactant X will be butane, right? A hydrocarbon. And then 4.1.5, write down the name or formula of product Y. Okay, so again, when we have a chemical equation, whatever that is on the left must be present in the right, right? It needs to be balanced. So we have butane, right? And then we add in bromine, and then we get 2-bromobutane. So in place of a hydrogen in butane, right, a hydrogen is replaced with bromine, right? And in place of bromine here, we're replacing it with a hydrogen. So Y will be hydrogen and bromine, right? So what is the it says the name of the formula of product Y. So let's not complicate our lives and try coming up with the name. Let's just say HBr, hydrogen bromide. 4.2 says 2-chlorobutane can either undergo elimination or substitution in the presence of a strong base such as sodium hydroxide. 4.2.1 which reaction will preferably take place when 2-chlorobutane is heated in the presence of concentrated sodium hydroxide in ethanol? Write down only substitution or elimination. So if you pay attention, you will realize that concentrated is in bold, right? So that will give us an idea of the knowledge we're supposed to apply. So what is the knowledge that we're supposed to apply? If the base is dilute, we go under substitution. If the base is concentrated, we go under elimination. So since here we are told that the base is concentrated, we are going to go under elimination. If it was dilute, we're going to go under substitution. And then 4.2.2 says write down the UPEC name of the major compound formed in 4.2.1. So we had 2-chlorobutane, right? And it is going under elimination. So when it goes under elimination, we are going to lose the chloro, right? And we're going to be left with but2ene. So 4.2.2, we have but2ene. And then 4.2.3 says use the structural formulae to write down a balance equation for the reaction that takes place when 2-chlorobutane reacts with a dilute sodium hydroxide solution. Now we're using a dilute base, right? And I've said that if we use a dilute base, we go under substitution, and if you use a concentrated base, we go under elimination. So let's write a structural formula for the substitution reaction that would take place. I will start by writing the structural formula of 2-chlorobutane, right? So we have 4 carbons, 1, 2, 3, and 4. And then on the second carbon, we have chloro. So let's have our Cl there. And everywhere else, we just have hydrogens, right? So let me just fill them in real quick, and then we move to the next step. So we're saying that we're using dilute sodium hydroxide solution, right? So let's have plus NaOH, right? And this is going to give us, now the substitution happens, right? How does it happen? This OH here is going to replace the halogen Cl, right? So if that happens, we're going to get 4 carbons again, and then in place of the Cl we have OH, right? Instead of a haloalkane, we now have an alcohol, right? And then we have a hydrogen, and then there goes another hydrogen. And then plus, we know that in a chemical reaction, whatever you have on the left, you should have on the right, right? So we're going to have NaCl. A group of grade 12 learners uses the reaction between calcium carbonate and hydrochloric acid to investigate one of the factors that influence reaction rate. They use the apparatus shown below. The reaction that takes place is represented by the following chemical reaction, and there it is given to us. 5.1 says identify the gas X, right? Yes, X here. So it's going to be pretty much simple to identify the gas X. That is because we know that on a chemical equation, whatever is on the left must be present in the right. So here, everything that is here, we're supposed to find it on the right. If we don't find it on the right given to us, then we know that it is part of X, right? So let's go ahead and do our analysis. So we have 1 calcium here, we also have 1 calcium here. We have 1 carbon, and then on the right hand side we don't have any carbon. So we know that carbon should be part of our X. And then we have 3 oxygens here, and then on the right hand side we only have 1. So we know that for that to balance, we need to have 2 oxygen being part of X, right? And then here we have 2 hydrogens. We have 2 hydrogens here as part of H2O, and then we have 2Cl, and then we have Cl2 here. So it seems like our gas that we're supposed to identify is CO2, carbon dioxide. Now let's move ahead and go to 5.2. 5.2 says 2 experiments are conducted by using the apparatus shown above. The conditions for each experiment are given in the table below. And then 5.2.1 says define in words the term reaction rate in terms of this investigation. And now we need to analyze the conditions that are given to us, right? So we have experiment 1 and 2, and then we have the same mass of calcium carbonate, right? So calcium carbonate seems to be our control variable, right? And then the state of division is also the same. So it's now we show that is the control variable. But then the concentration of HCl is different in experiment 1 and 2. So HCl is our independent variable. So our dependent variable will be our reaction rate. And then 5.2.1 says we should define reaction rate in terms of this investigation. So we're basically investigating the influence of concentration on reaction rate, right? So here in this reaction, HCl is part of the reactants. So we are going to be measuring how fast or how quick HCl is decreasing per unit time, right? So if we would define reaction rate in terms of this investigation, we would say that is the decrease in concentration of HCl per unit time, right? Because we know that the reaction rate is the change in concentration of products or reactants per unit time. But then here on this investigation is the decrease in concentration of HCl per unit time. So you write that in full, but I'm just going to demonstrate that is the decrease in the concentration of HCl per unit time. But you're supposed to write it in full. And then 5.2.2 says from the table above, write down the independent variable for this investigation. We've talked about that. The independent variable is the concentration of HCl. We know from math that the X is the independent variable and the Y is the dependent variable. The X in this instance is the concentration of HCl. That's what we are changing. And then the reaction rate is the dependent. It's what we are measuring, is our result, right? And then 5.2.3 says give a reason why the learners must use equal masses at the same state of division of calcium carbonate. So we need one variable to be changing. If we're changing too many things, then it cannot be clear how what we are changing is influencing the reaction rate. For instance, if you use lumps on one experiment and on the other one you use powder, and then the reaction rate changes, how do you know that it is because of the concentration or the lumps or both or neither, right? It just becomes too complicated. So we need only one variable to be changing, right? In that way, the investigation is fair, right? It becomes a fair test or a fair comparison. So 5.2.3.1, we need the masses and the state of division of CaCO3 to stay the same, so that the experiment can be fair. Let's move to 5.3. 5.3 is saying the learners observe that the reaction rate is higher in experiment 2 than in experiment 1. Let's go back to our table again. Experiment 2, we have 0.4 mole per decimeter cube as the concentration of HCl, right, compared to 0.2 in experiment 1. We use the collision theory to explain this observation. So we've increased the concentration, right, and it turns out that the reaction rate increases. Obviously, that is because by collision theory, when you increase the concentration, you will have more particles, right? When you have more particles will have more kinetic energy that is equals to or greater than the activation energy. As a consequence, we have more effective collisions per unit time, and the reaction rate increases. So let me just put that in words. And there it is. Let's move forward to 5.3.2. So we're essentially saying that higher HCl concentration mean more particles per unit volume, right? And then if we have more particles per unit volume, then more particles will have EK being greater or equals to EA, right? EK being the kinetic energy, and then EA being the activation energy. So we'll have more effective collisions per unit time. If we have more effective collisions per unit time, then rate of reaction increases, right? 5.3.2 says, refer to experiment 2 and calculate the volume of HCl in centimeter cube that reacts with CaCO3. So let's go back to our equation and let me just copy it. So we have CaCO3 plus HCl. I think we have 2 here, giving us CaCl2 plus X plus H2O. So we need the volume of HCl, and then we have the mass of CaCO3, right? So we have mass of CaCO3. From that mass, we can find the number of moles of CaCO3, right? And with that number of moles, we have the concentration. We can use that number of moles to find the number of moles of HCl through the balancing coefficients. And with those number of moles and the concentration of HCl we are already given, we can find the volume, right? So let's go ahead and do that. So we know that the number of moles is the mass divided by the molar mass. The mass of CaCO3, it is said to be 4 grams, right? And then the molar mass of calcium carbonate is 100, right? And then 4 divided by 100 will be 0.04 moles. So now we can use the balancing coefficients to find the number of moles of HCl. So what we can do, we can say that the number of moles of CaCO3 divided by the number of moles of HCl is equals to 1 divided by 2. So the number of moles of calcium carbonate, 0.04, divided by the number of moles of HCl will be equals to 1 divided by 2. So we basically cross multiply in here, right? So the number of moles of HCl will be equals to 0.08 moles, right? So now from this number of moles, we can find the volume of HCl, right? So let's come to the volume of HCl. So we know that the concentration is equal to the number of moles divided by the volume. We know the concentration is given to us in experiment 2 is 0.4, and then number of moles is 0.08, right? And then we have our volume. So we basically cross multiplying here and dividing both sides by 0.4. So we're gonna have the volume being 0.08 divided by 0.4. So what is 0.08 divided by 0.4? That is 0.2 decimeter cube. But then we don't need our value in decimeter cube. It is said to be, we are asked to give it in centimeter cube, right? So from decimeter cube to centimeter cube, you multiply by 1,000. 0.2 multiplied by 1,000 is 200 centimeter cube, right? And then 5.4 says schedule potential energy versus reaction coordinate graph for this reaction. Label the axis and indicate the following on the graph. We don't have the values of the activation energy, heat of reaction, and activated complex, and so on. So here they're asking us to just have a basic graph, right, of how a potential energy graph would look like for this reaction. I think what we just need to look at is whether this reaction is endothermic or exothermic. So here we have potential energy, right? Potential energy. Let me just scroll up and look at the reaction. So the reaction is exothermic because the enthalpy change is less than 0, right? So the energy of the products must be less than the energy of the reactants. So if the reactants are starting somewhere here, and then we go up, then yeah, our products are supposed to be somewhere here. In this way, our enthalpy change will be 0, right? So let's denote the enthalpy change here. So we're gonna have an enthalpy change of less than 0, and then our activation energy. Let's denote our activation energy here. So we have EA, and then up here we have our activated. The following equation represents a key reaction in the preparation of sulfuric acid. The process of the reaction is controlled in such a way that the temperature inside the container remains between 370 degrees Celsius and 550 degrees Celsius at all times. 6.1 says what is represented by the double arrow in the equation. In chemistry, we know fully well that if we have a double arrow, it simply means that the reaction is reversible, right? So 6.1, you just write the reaction is reversible, and you get your 1 mark. And then 6.2 says, why is this reaction known as the contact process? It is known as the contact process because the reaction occurs in the presence of a catalyst, right? So the reaction is in contact with the catalyst, and therefore is known as the contact process. Now the question you might ask is, which catalyst do we need for this reaction? We need vanadium oxide, right? So the catalyst for our contact process is vanadium oxide, spelled vanadium oxide. But that's not what the question is asking us. The question just wants us to explain that it is known as the contact process because we are in contact with a catalyst, and you get your 1 mark. And then 6.3 says explain what the temperature is preferably not, and then 6.3.1 lower than 370 degrees. So they're telling us that for this reaction we need the temperature to be at least greater than 370 degrees. We need the reaction to be greater than 370 degrees because if the temperature is too low, right? If the temperature is too low, then the yield from the reaction will not be enough, right? Because you know that to increase the reaction rate, we need to increase the temperature, right? So that our yield can go up, right? So the temperature, if it's too low, the yield won't be enough. 6.3.2 says explain what the temperature is preferably not higher than 550 degrees Celsius. Let's look at our equation. Delta H is less than 0, right? So if you increase the temperature too much, then the reverse reaction will be favored. So you'll be basically converting your products back into reactants, and that's not what we want to achieve, right? So you must keep the temperature high enough, but you must not make it too high, because now the reverse reaction will be favored and we will get the reactants again. So here we're saying that a high temperature favors an endothermic reaction, right? A high temperature, temp favors an endothermic reaction, right? Endothermic reaction. And then clearly the reverse reaction is endothermic, right? So our reverse reaction is endothermic. So if we increase the temperature, less products will be formed, right? So we're gonna have less products being formed. And then let's move to 6.4. 6.4 is saying, for the process above, the following information is obtained from the analysis of the equilibrium mixture at 400 degrees Celsius. The volume of the container is 200 decimeter cube. The initial quantity of SO2 is 50 moles, and then the equilibrium quantity of SO3 is 22 moles, and then the Kc at 400 degrees Celsius is 7.328. Use the information above to calculate the initial mass of oxygen that was used for this reaction. So we're still going to follow the usual technique we use when we want to find Kc, right? But then the only difference here is that we're going to have a value for Kc. We're going to be solving for the oxygen, basically, right? For the number of moles of the oxygen. And then from the number of moles of the oxygen, we're going to be able to determine the mass, therefore. So we have 2SO2 reacting with O2, and then this is giving us 2SO3. We know that the reaction is reversible, so let's have that there. So here we need the initial number of moles, right? Here we need the change, and here we have the moles at equilibrium, right? And then here we have the concentration. So initially we had 50 moles of SO2, so there goes our 50. And then for O2 we're not given, right? That's what we need to find so that we can consequently find the mass. And then for SO3 we're starting with 0, right? And then at equilibrium we have 22. So at equilibrium for SO2 we have 22, right? So the change here was plus 22. So now we need the change for O2, right? The balancing coefficient here is 2 and here it's 1, right? We usually don't write it, but we know there's a 1 here. So we basically dividing 22 by 2, which will give us 11, right? So if we were given 11 here and we're finding the number of moles of SO3, then we're gonna multiply by 2. For SO2, the balancing coefficients are the same, so we're gonna have 22 here, but we're converting the reactants to products, right? So here we're gonna have minus 11, here we're gonna have minus 22. So what is 50 minus 22? That is 28. And then what is x minus 11? X minus 11. And then now the concentration at equilibrium, right? So we're dividing by a volume of 200 decimeter cube. So we have 28 divided by 200, x minus 11 divided by 200, and then we have 22 divided by 200. So now we can see that the Kc is equals to the concentration of the products divided by the concentration of the reactants. So if we go on with that, our product will only have SO3, right? So we're gonna have 22 divided by 200 to the power 2, right? The balancing coefficient divided by the reactants. So we have 28 divided by 200 for SO2, right? To the power 2 multiplied by x minus 11 divided by 200 to the power 1, the balancing coefficient. But we given the value of Kc, we know that it is 7.328. So now we have to solve for x. How are we gonna do that? What we can do here, we can say that x minus 11 divided by 200 is equals to 22 divided by 200 squared divided by 28 divided by 200 squared multiplied by 7.328. right? This step here might be confusing to some, but it's mathematically true, right? You can check it out and see if it works. So every time when you're solving a question like this in KC, you can just take a term in the denominator and swap it with the term on the other side of the equation, right? It's true. And then from here, so let's multiply both sides by 200 so that we can get rid of this 200 here, right? So if we do that, we're gonna have x minus 11 is equals to 22 divided by 200 again squared divided by 28 divided by 200 squared multiplied by 7.328, and then we multiply in everything by 200, right? So now you can see that you just add 11 to both sides and you determine x. So if you add 11 to both sides, so let's take this entire expression, right? And then we say plus 11. So now we can erase this minus 11 here. We get x being equals to 27.849, right? So now we can use those number of moles to calculate the mass of O2 initially, right? So we know that the mass is equals to the number of moles multiplied by the molar mass. So that will be 27.849 multiplied by 16 multiplied by 2. Yes, so that will give you 891.167 grams. This is a bit lengthy. You can rewind the video so that you can get more clarity. So 6.5, last but not least, says the temperature for the process above is increased to 500 degrees Celsius. Consider the graph, and then there we have a graph. Which reaction, forward or reverse, is represented by the dotted lines? First of all, let's focus on the reverse reaction. We know that the reverse reaction is endothermic. So when we increase the temperature, the reverse reaction should be favored the most, right? More especially above 500 degrees Celsius. When we close to reaching that 550 degrees Celsius, we're not supposed to reach for this reaction because the products will be too little, right? So when we increase the temperature, the reverse reaction will be favored, but the forward reaction will also be favored, but the reverse reaction will be favored more because it is endothermic. So hence the dotted line and the other line, they all go up, right? But then you can see clearly that this solid line goes up way above the dotted lines, right? So it is more favored. Hence the solid line is the reverse reaction. So the forward reaction is the dotted line. So the question is asking us to determine which line is the dotted line. The dotted line is the forward, right? Because we know that the reverse will be favored more than the forward if the reverse reaction is. The following apparatus is used for the titration of a dilute alkali with a dilute acid, and we're given a balanced equation And 7.1.1 says, what type of a reaction takes place when an acid is added to an alkali? An alkali is basically a base, right? So we have an acid and base reaction. So 7.1.1 acid and base reaction. Another name for an acid and a base reaction is neutralization, right? So you can write acid and base, or you can write neutralization. Now let's move to 7.1.2, which says that write down the name of the dilute alkali. So the acid is H2SO4, right? Which is basically sulfuric acid. Ba is barium, right? And then OH, you usually pronounce it as hydroxide, right? If you remember, if we have NaOH, this would be sodium hydroxide, right? So this will consequently be barium hydroxide. So here 7.1.2, we have barium hydroxide. 7.1.3 says, name the pieces of apparatus labeled X. So here's X here. You should be familiar with X at this point of time, right? X is a burette. It's essentially a glass tube, right? With readings on it, and it has a turning plug here, right? To control the amount you're putting in on your beaker or whatsoever you're using. So 7.1.3, we have a burette. And then 7.1.4 says methyl orange is used as an indicator. What will you observe in Y when the acid is added before the endpoint is reached? So before we add any acid, right, you are going to basically have a base, right? If you add methyl orange to a base, then the methyl orange is gonna turn yellow. So what we are going to observe between before the endpoint is reached is that the methyl orange turns yellow, and then as we add more acid, it will gradually turn to orange as we reach a pH of around 7. And then if you keep on adding more acid, and now the solution actually becomes acidic, then the methyl orange will turn red. So for 7.1.4, the methyl orange turns yellow because we added into a base, and gradually turns orange. And if you keep adding more acid and your solution becomes acidic, it will consequently turn red. And then 7.1.5 says, state whether each of the following increases, decreases, or remains constant while the acid is being added before the endpoint is reached. So back to the basics. What's an acid? An acid is a proton donor. So when we increase the acid, we increase in H+, right? So what will happen to Ba to the 2+, right? We won't have any effect on Ba to the 2+ when we increase the acid, right? So Ba2+ will remain constant, right? And then what will happen to OH minus? The concentration of OH minus will go down when we add H+. Why am I saying that? So before we started adding the acid, right, we just had BaOH2 giving us Ba to the 2+ plus 2OH minus, right? So when we add the acid H2SO4, the Ba2+ will react with SO4 2 minus, and then the OH minus will react with 2H+. So the more we add the acid, the more the concentration of OH minus decrease, right? Because OH plus H is clearly H2O. So here for OH minus is going to decrease. So for pH, we know that the pH is equals to minus log of H plus. The more you increase the concentration of H plus, the lower the pH will be, right? So as we increase H plus, the pH will consequently decrease. And then now we can do 7.1.6. 7.1.6 says that during the reaction, 50 centimeter cube of the dilute alkali reacts completely with 30 centimeter cube of the dilute acid. So the dilute alkali is reacting completely. That tells us that the dilute alkali is our limiting reactant, right? And then the question goes on to say, calculate the mass of barium sulfate that will form during the reaction if the concentration of the dilute alkali is 0.1 mole per decimeter cube. So we have the dilute alkali BaOH2, right? And then we are given the concentration. It is said to be 0.1 mole per decimeter cube, and then we are given the volume, which is said to be 50 centimeter cube. So if we find the number of moles of BaOH, then we're gonna be able to use those number of moles to find the number of moles of barium sulfate, right? And from the number of moles of barium sulfate, we'll consequently be able to find its mass, because that's what the question is asking us to do, right? So here we're gonna have the concentration is equal to the number of moles divided by the volume. If you make the number of moles a subject of the formula, you get concentration multiplied by volume. So what's the concentration? The concentration is 0.1, and what is the volume? The volume is 50 centimeter cube, right? But we'll deal with decimeter cube. So here we're going to have 50 divided by 1,000. So 50 divided by 1,000. So we basically have 5 divided by 1,000, which will be close to 0.005 moles, right? So if we go back to our equation again, the balancing coefficients, we have 1, 1, 1, right? So the number of moles are basically equal for all those three that I just indicated there. So the number of moles of BaOH2 will be equal to the number of moles of BaSO4. So that will be 0.005 mole, right? Now we can calculate the mass of barium sulfate. We have the number of moles, and the molar mass we can get it from our periodic table. So now we know fully well that the number of moles is equal to the mass divided by the molar mass. If you make the mass of the subject to the formula, you get number of mole multiplied by the molar mass. So what is the number of mole? What we just calculated, right? So we have 0.005 multiplied by the molar mass of barium sulfate. If you add the molar mass of barium and SO4, that will give you 233. So 233 multiplied by 0.005, that is 1.165 grams. So the mass of the barium sulfate that will be formed will be 1.165 grams. I hope that is clear. Let's just recap for the last time. We're given the concentration and the volume of the dilute alkali, or barium hydroxide, right, which was used, and then we figured out that it's our limiting reactant, right, because we are told that it reacts completely. So from there we find the number of moles of the alkali, the dilute alkali, and we use those number of moles to find the number of moles of the barium sulfate, right? And from the number of moles, we calculate in the mass here, right? High school chemistry is basically finding the number of moles of one reactant and using it to find the number of moles of the other, and from there you'll find either the concentration or you'll find the mass. And then 7.2 says 2 test tubes contain solutions of NH4 NH4 plus, I think, and CH3COONA. Their pH values are less than 7 and greater than 7 respectively. Write down the following rewrite the following hydrolysis equation in the answer book and complete them to explain this behavior. So for NH4 plus, we are told that the pH is less than 7, right? So if it is less than 7, it is acidic. And if it's acidic, then it's a proton donor, right? So that NH4 plus is supposed to lose a proton, it's supposed to lose one hydrogen, right? So here we're gonna have NH3, right, instead of NH4, because now we have lost a hydrogen, plus H3O plus, right? And then that's basically what you're being asked to do. And then now let's pay our attention to 7.2.2. It is said to have a pH of greater than 7. What does that tell us? It tells us that it is basic, so it's supposed to gain a proton, right? So we're gonna have CH3COOH, right? There we go, we have gained a proton, plus now the proton is coming from H2O, right? So the H2O now will be OH minus. And then now so the hydrogen that NH4 plus lost came to H2O, right? So hence here we have H3O plus. Sets up an electrochemical cell based on the following reaction: aluminium plus copper 2 plus ion, giving us aluminium 3 plus ion plus copper. And then 8.1 says identify the type of chemical cell represented by this reaction. We only have two options here. We have either galvanic cell or electrolytic cell. Clearly, this is a galvanic cell. Why am I saying clearly? We don't have an equation for an electrolytic cell, right? We don't have an equation like the one we have here. That is because when an electrolytic cell, the electrodes are not reacting. So you cannot have such an equation. You can only have such an equation for a galvanic cell. So the answer for 8.1 is galvanic cell. Well, there's two names for a galvanic cell. It's either it's galvanic cell or you use voltaic cell, right? And then 8.2 says represent this cell by writing its cell notation. So what's the standard formula? What's the formula for a cell notation for a galvanic cell? So you have the anode, the salt bridge, and the cathode, right? So we have our equation here, which I've circled in blue, right? Now let's identify what the anode is and what the cathode is, right? So we know from definition that at the anode, that's where oxidation happens. We lose electrons, right? So if you look at this formula here, clearly aluminium is losing electrons and becoming aluminium 3 plus. And then at the cathode, that's where reduction happens, gaining of electrons. Copper 2 plus is gaining electrons and becoming copper, right? So at the anode, we have aluminium, and then at the cathode, we have copper, right? So our standard cell notation will then become aluminium, and then we have aluminium 3 plus our salt bridge, and then the contents of the cathode, right? Which is copper 2 plus and copper. Well, if you write this, you get your full marks, but you can go a step forward and give the states, right? You can see that for the copper here, it's a solid, so you can put that on your cell notation. But then we don't want to make any unnecessary mistakes, so let's just leave it like this and go to the next question. You are gonna get your full marks. Do the electrons in the external circuit flow from the aluminium to the copper, or from the copper to the aluminium electrode, right? So what do we know about a galvanic cell? We know that the electrons in the external circuit of a galvanic cell, they flow from the anode. They flow from the anode to the cathode, right? We have already identified what the anode is and what the cathode is, right? So clearly they will be flowing from aluminium to copper, right? From the aluminium electrode to the copper cathode. Thank you. And then 8.4 says, for this cell, write down the half reaction that takes place at the anode. At the anode, oxidation happens, loss of electrons, right? So aluminium tends to aluminium 3 plus, right? Given in our equation here, right? But then it will be aluminium 3 plus 3 electrons, right? Because clearly it's losing 3 electrons and becoming 3 plus. So we're supposed to add 3 electrons here. So if it was becoming aluminium 2 plus, then we're also going to add 2 electrons. That's how you sort of do it. And then this makes total sense, right? We add the anode, oxidation happens, and we are losing our electrons, right? But then in the exam guideline, they don't give you full marks if you write it like this. You actually get 1 out of the 2 marks. The way they want you to write it, they want you to say that aluminium 3 plus 3 electrons is giving us aluminium, right? But then with the arrow pointing backwards. I don't know why this is, because this first option here makes total sense. The second option makes sense too, because it's basically the same thing. Let's move to 8.5. 8.5 says, calculate the initial EMF of the cell under standard connections. We know that the formula here that we have is that the initial EMF of the cell is equals to the electropotential at the cathode minus the potential at the anode. So for a galvanic cell, you're supposed to get an EMF of positive, right? Because this reaction is spontaneous. You don't need any external charge to initiate it. So the mistake that people usually make is that they switch the 2 numbers they're supposed to use and get a negative value. So I'm telling you that if you get a negative value, just know that you did something wrong. There's no way you're supposed to get a negative value for the EMF of a galvanic cell under standard conditions, right? So now at this point, you go to the back of your question paper, right? You're gonna get a table with the potentials for different elements, right? So at the cathode, we already said that we have the copper, right? So we have to go to a periodic table and see which value the copper has, right? The copper has a value of 0.34. Another mistake people do, we have copper, right? Copper giving us copper 2 plus 2 electrons. On the data sheet, there's another copper that gives you copper plus 1 electron, and then it has a different value, and then most of the time people will pick the wrong copper, right? So you have to pay attention. Are you picking the right value? You have to make sure that you are picking the right value for copper 2 plus. If you're given copper plus, then you have to pick the corresponding value of copper plus. The value of copper plus, I think, is 0.16, and then for copper 2 plus is 0.34. So you have to make sure that you're picking the right value. And then minus the potential at the anode. At the anode, we have aluminium, giving us aluminium 3 plus 3 electrons, right? And then it has a negative value. It has minus 1.66. Go at the back of your question paper and you're gonna see these values I'm talking about. They are there on your question paper. So now we basically have 0.34 plus 1.66, right? Which will give you 2 volts. So then initial EMF of this cell under standard conditions is 2 volts, right? If we were given an electrolytic cell, then we will be expecting an initial EMF that is negative, right? Let's move to 8.6. 5 grams of AlCl3 is dissolved in the aluminium half cell of the standard cell. What will be the effect on the cell potential? Choose from increase, decrease, or remain the same, right? So we know that under standard conditions, this is the formula we use. This formula we use for 8.5, right? But then right now, we no longer have those standard conditions. So we cannot just say remain the same because this is the formula we use and any of those factors and none of those factors affect this formula. We cannot say that because now we don't have the standard conditions. One of the standard conditions is that the temperature is at 25 degrees Celsius and that the concentration is 1 mole decimeter cube. But then when we add AlCl3, we are increasing the concentration of something, right? Now let's break down what concentration we are increasing. Let's go back to our formula we have. So AlCl3, when it breaks down, will give you Al3 plus 3Cl minus. So clearly, when we add 5 grams of AlCl3, we are increasing the concentration of Al3 plus. But then what effect will that have on our EMF, right? So that's where the new knowledge comes in. The new knowledge is that on this equation that we have, if the forward reaction is favored, the EMF is going to increase. But then if the reverse reaction is favored, the EMF is going to decrease. Clearly, we have increased the concentration of Al3 plus. So the reverse reaction will be favored. Le Chatelier's principle. So when the reverse reaction is favored, the EMF is supposed to decrease, right? So here for 8.6.1, we have decrease. And then 8.6.26, explain your answer to question 8.6.1. Al3 plus, right? The concentration will increase, right? And then when it increases, Le Chatelier's principle, the reverse reaction will be favored. So reverse reaction is favored. Now what will happen when the reverse reaction is favored? The EMF will decrease. So yeah, we have EMF will decrease. Now we can move to 8.7. 8.7 says what energy conversion takes place when the cell is in operation. For a galvanic cell, we convert in chemical energy to electrical energy. And then for an electrolytic cell, we convert in electrical energy to chemical energy. Copper is obtained by electrolysis using a thin, pure copper cathode and an acidified solution of copper sulfate, clearly demonstrated on our schematic. And then 9.1 says, at which electrode will pure copper be deposited? Write only A or B. So back to the basics again. In electrolysis, we have 2 electrodes connected to a power source, right? Clearly, this will be the positive terminal and this will be the negative terminal. Now the question you have to ask yourself is that which electrode is connected to the positive terminal and which electrode is connected to the negative terminal. In an electrolytic cell, the anode will be connected to the positive terminal. So here we know that electrode B is our anode, and then consequently electrode A is our cathode. But that's not what the question is asking us. At which electrode will pure copper be deposited? Right, only A or B. Where the pure copper is deposited, it's where reduction happens, the gaining of electrons that takes place at the cathode, right? So from that information here, our answer would be A, right? That's where the pure copper will be deposited, because A is our cathode, and that's where reduction takes place. And then 9.2 says write down the half reaction for this cell. We have pure copper. It needs to be deposited somewhere. We're saying that it takes place at the cathode, and at the cathode, that's where reduction takes place. So we're gonna have copper 2 plus 2 electrons, giving us copper. That's our reduction half reaction for this cell. Now let's move to 9.3. 9.3 says that use the graph to calculate the percentage purity of the impure copper that was used as the cathode. The mass of the impurities formed in an hour is 15.8 grams when a constant current is used. Right, now let's go back to the basics. We have percentage purity, right? Percentage purity, that is mass of pure sample, right, divided by the mass of the impure multiplied by 100. But in this question, it's not really that clear, so we have to break it down, right? The mass of the pure sample will be the mass deposited at the cathode, right? So here we're gonna have mass deposited, and then mass of impure will be mass deposited plus the impurities that are left behind, right? So here we have mass deposited plus the mass of the impurities, right, multiplied by 100, because we have this chunk of an impure sample, and then some of that amount gets deposited at the cathode, so we know that that amount is pure. But then the mass of the impure sample as a whole will be the mass of the impurities plus the mass of the deposited. So we are told that after an hour 15.8 grams is deposited at the cathode, right? So we're gonna have 15.8 divided by 15.8 mass deposited plus the mass of the impurities. The mass of the impurities formed in an hour is 15.8 grams, right? So we're basically gonna be finding mass deposited. So we're gonna have mass deposited, which we're going to find divided by 15.8. That is for impurities, right? Plus mass deposited again. So we have mass deposited. We're still multiplying this entire number by 100. So now our duty is to find the mass deposited, right? If we go back to our sketch here, you're gonna see that the number of moles deposited in 1800 seconds is 0.25, right? But then here on our equation, we're given the mass of impurities in an hour, right? So we have to multiply this 0.25 to find the number of moles deposited in an hour, right? We have the impurities in an hour. We have to find the number of moles in an hour. So now we can say that the number of moles is equals to mass divided by molar mass. So we're looking for the mass, so we're gonna say the number of moles multiplied by the molar mass. So what is the number of moles? The number of moles in an hour will be 0.25 multiplied by 2, right? We are given the number of moles in 30 minutes. We want the number of moles in an hour, so we simply multiply by 2, right? And then the molar mass, we're looking for the molar mass of copper, which is 63.5, and then when you multiply that 2, you get 31.75 grams, right? Our percentage purity, right, will then be equals to 31.75, which is the mass deposited divided by 15.8, which is the mass of the impurities, plus the mass deposited again, which is 31.75 multiplied by 100. And then if you punch that in your calculator, and that will give you 66.67%. Now let's move forward to 9.4. 9.4 says the copper sulfate is an electrolyte and the concentration remains constant for the duration of the reaction. 9.4.1, define an electrolyte. An electrolyte is a solution that conducts electricity through the movement of ions. An electrolyte is a solution that conducts electricity through the movement of ions. And then 9.4.2 says explain why the concentration of the solution remains constant. The concentration of the solution remains constant because the rate of oxidation is equal to the rate of reduction. The rate of losing electrons is equal to the rate of gaining electrons, and as a consequence, the concentration of the solution. Which nutrients does fertilizers contain? We know fully well that fertilizers contain NPK, right? Or if you want to write it in full, we have nitrogen, nitrogen gas, and then we have phosphorus, and then we have potassium, represented by K, potassium. And then 10.1.2 says which of the three nutrients is neither produced or mined in South Africa? So we have NPK, right? Nitrogen gas. That's a gas, right? We find it everywhere. It's basically dry air. So we're definitely not talking about nitrogen. Now the solution is between phosphorus and potassium, right? Phosphorus is mined in Palawura by a company called Fosco, right? So the nutrient that is either mined or produced is potassium, right? And then 10.1.3 says one of the primary nutrients is mined in South Africa. State the mineral form in which it is found. We have already stated that phosphorus is mined in South Africa, in Palawura, right? The mineral form in which it is mined, we find it in the form of phosphate, right? And then 10.1.4 says, name an industrial process by which the third primary nutrient not mentioned in 10.1.2 and 10.1.3. So we mentioned potassium and we mentioned phosphate, right? Phosphorus. So we're talking about nitrogen. So which industrial process makes nitrogen available as a fertilizer? That is the Haber process, right? So we have a Haber process there. And then 10.2 says the use of fertilizer has one important negative effect called eutrophication. Define eutrophication. This is more of a life science term, right? It says that it is the process by which an ecosystem can be a river, a dam, and so on, becomes enriched with inorganic nutrients, especially phosphorus and nitrogen, resulting in excessive plant growth, right? A process by which an ecosystem becomes enriched with inorganic nutrients, especially phosphorus and nitrogen, results in excessive. resulting in excessive plant growth. And then 10.3, a farmer plans to plant maize. His research shows that he needs 18 kgs of nitrogen, 3 kgs of phosphorus, and 3.25 kgs of potassium in the soil to produce 1 ton of maize per hectare. A fertilizer company advises him to use 100 kgs of fertilizer A that has an NPK ratio of 4:1:1, or 2 packs of 50 kg of fertilizer B that has an NPK ratio of 7:2:2. Do the necessary calculations to advise the farmer on which fertilizer he should buy to avoid overnutrition of the plants. Okay, so to avoid overnutrition of the plant, so we want the fertilizer that is closest to the research the farmer is proposing, right? So the farmer says that let's say we have NPK. The farmer says he needs 18 kgs of nitrogen, and then he needs 3 kgs of phosphorus and 3.25 kgs of potassium. So let's go ahead and calculate the kgs from fertilizer A and fertilizer B for nitrogen, potassium, and phosphorus, and see what we get, right? So when we talk about the NPK ratio, so let me put fertilizer A here. So we have an NPK ratio 4:1 and then in bracket we have 36, right? So 4:1 is the ratio of the nutrient, and then the number in the bracket is the actual percentage of fertilizers in the entire bag. So if we want to find the kgs of nitrogen, right, because we know that it says NPK, then we're going to have 4 divided by 6, the total numbers we have as ratios, right? So we have 4 divided by 6 multiplied by 36, and that will give us the mass of nitrogen in that fertilizer. So 4 divided by 6 multiplied by 36 is 24. And now we can go to phosphorus. So the amount of phosphorus in kg will be 1 divided by 6 multiplied by 36. 1 divided by 6 multiplied by 36, that is 6 kgs, right? Now we can go to potassium. We just did phosphorus, right? So we're going to have 1 divided by 6 multiplied by 36, because the ratio of potassium is also 6, right? So that will also be 6 kgs. So now let's compare these kgs with what the farmer is looking for, right? The farmer is looking for 18. Fertilizer A has 24 for nitrogen, right? It's looking for 3 kgs of phosphorus. This fertilizer A has 6 kgs, and then for potassium it's looking for 3.25. Fertilizer A has 6 kgs. So it's really above what the farmer is looking for. But then let's look at option B and see if it's any better, right? So for option B, yes, option B here, we have the ratio at 7:2:2, and then the actual amount is 15%. And then this is for a 50 kg bag, right? But then the dealer at the store is saying that I should use 2 of these 50 kg bags. So if it's using 2 of these 50 kg bags, then you can write the ratios as 14:4:4, and then in bracket you put 30, right? Or instead of doing that, you calculate the mass as it is, and then you just multiply it by 2 at the end, right? So let's do that. So for nitrogen, we're going to have 7 divided by 7 plus 2 plus 2, that is 11, multiplied by 15. And that is 9.54 kgs, right? And this is for a 50 kg bag. So because they're saying you should use 2, we can multiply that number by 2, right? So that we can get the amount for 100 kgs bag. So for 100 kg, we're going to have 19.09 kgs, right? This is for 100 kg bag, or 250 kgs, right? And then now let's go to phosphorus. So phosphorus, we're going to have 2 divided by 11 multiplied by 15. We're going to get 2.7273 kgs, right? And then obviously we're going to multiply that by 2 so that we can get the amount if we use 2 bags. If you multiply by 2, you get 5.45 kgs, right? And then for potassium, it will be the same as phosphorus, right? Because they have the same ratio. So here we also have 5.45 kgs, right? So now let's do our comparison. The farmer doesn't want overnutrition, right? So we should pick a fertilizer that is closest to what the farmer is looking for, right? For fertilizer B, for nitrogen, we have 19.09 if you use 2 bags, right? And then for phosphorus, we have 5.45 if you use 2 bags. And then for potassium, we have 5.452. And that is closer to what the farmer is looking for compared to fertilizer A, where you have 24 for nitrogen, 6 for phosphorus, and 6 for potassium, right? So here, I'm advising the farmer to pick fertilizer B.